There are two silent stars gliding with purpose in the Earth's orbit. One is the familiar International Space Station, our handhold in the void. The other is China's enigmatic Tiangong, the Heavenly Palace. These two outposts are not merely different stations. They are rival visions for the future of humanity. The ISS is a global laboratory, a symbol of cooperation built to study our own fragile biology and gaze back at the home we came from. But Tiangong is something else entirely. Born from exclusion, it is a self-reliant forge quietly perfecting the tools not just to explore the cosmos, but to industrialize it. This fundamental schism is playing out 400 kilometers overhead. While astronauts on the ISS meticulously catalog the slow decay of the human form in zero gravity, taikonauts on Tiangong are mastering the alchemy of recycling their own exhaled breath back into rocket fuel, preparing for a future on Mars. This is the story of humanity's great divergence in the void, a choice being made right now between two futures for our species. One path looks inward, obsessing over our biological limits. The other looks outward, forging the technology to make those limits obsolete. Today we pull back the curtain on the Heavenly Palace. We will uncover the audacious science, secret history, and sheer ambition driving these two civilizations in the sky to understand what their rivalry means for the future of us all. Journeys like this are best taken together. If you find value in exploring these cosmic narratives, a simple click of the like button lets us know we're on the right path. And as always with our videos, the visuals are here to add context, but they aren't necessary to follow along. Settle in, let us know where you're joining from in the comments, and let's dive in. The International Space Station, the ISS. For over 2 decades, it has served as our collective foothold in the cosmos. A sprawling, magnificent symbol of what we can achieve when we look past our terrestrial squabbles and towards a common goal. It is a floating United Nations, a scientific cathedral built in the vacuum by the hands of former Cold War adversaries. Its purpose, as we have come to understand it, is one of pure discovery, to probe the mysteries of microgravity, to study our planet from a divine vantage point, and to learn how the human body endures the unforgiving environment of space. It represents a grand, sprawling, and inclusive vision of our future off-world. But there is another light. A second station. Newer, sleeker, and to much of the Western world, far more enigmatic. It is called Tiangong, the Heavenly Palace. It is the sole property and project of the People's Republic of China, and it has been permanently crewed since 2021. While the ISS broadcasts its experiments and its daily life with a spirit of open, global outreach, Tiangong operates with a quieter, more focused intensity. Its presence marks a profound shift in the story of humanity's expansion into the solar system. For the first time since the dawn of the space age, we have 2 independent, permanently inhabited human civilizations in orbit, and they are not built in the same image. They are the orbiting manifestations of 2 fundamentally different philosophies, 2 divergent strategies for what comes next. The ISS is a destination, a laboratory for understanding the frontier. Tiangong is a waypoint, a workshop for equipping the pioneers. To understand the Heavenly Palace, one must first understand why it exists in isolation. It was not born of a simple desire for a national status symbol. It was born of necessity, forged by the fires of geopolitical exclusion. A piece of American legislation, the Wolf Amendment, passed in 2011, effectively barred NASA from any bilateral cooperation with the Chinese space program, citing national security concerns. The door to the international club was locked and bolted. So China did not knock. It simply went away and built its own, more advanced clubhouse. This single political act cleaved the future of space exploration in 2. While the ISS stands as a monument to reconciliation, Tiangong stands as a testament to self-reliance and the unyielding force of national ambition. It is a consequence of 21st century rivalries, not a celebration of 20th century resolutions. This divergence is reflected in every aspect of their design and mission. The ISS is a behemoth assembled over decades at a cost exceeding $150 billion, a financial burden shared, albeit unevenly, by its 15 partner nations. It is a magnificent aging giant, a testament to a bygone era of space construction. Tiangong, by contrast, was constructed with breathtaking speed and efficiency. Its core module and 2 laboratories launched and assembled in under 2 years, at an estimated cost that is a mere fraction of its international counterpart. It is smaller, more modern, and bristling with a higher degree of automation, reflecting a leaner, more agile approach to orbital infrastructure. But the most profound difference is not in the hardware, it is in the intent. The science conducted on the ISS is broad, reflecting the diverse priorities of its many members. It is a cosmic university, pursuing knowledge across a vast curriculum for the general benefit of humankind. The research aboard Tiangong is different. It is not a curriculum, it is a blueprint. Every experiment is a meticulously chosen piece of a much larger puzzle, a series of technological dress rehearsals for a future that extends far beyond low Earth orbit. While ISS astronauts study bone density loss, Tiangong taikonauts are perfecting the systems to create fully closed-loop life support, capable of recycling every drop of water, every molecule of oxygen, and turning waste into resources. While the ISS hosts experiments on the nature of fire and zero gravity, Tiangong is testing new methods of artificial photosynthesis, turning the carbon dioxide exhaled by its crew not just into breathable air, but into the chemical precursors for rocket fuel. This is not science for the sake of science. This is strategic research and development on an unprecedented scale. They are not just learning to survive in space. They are mastering the technologies of self-sufficiency, of in-situ resource utilization, of off-world manufacturing. The Heavenly Palace is not a laboratory in the traditional sense. It is a forge, and what is being hammered out on its anvil is the toolkit for cosmic industrialization. It answers not the broad question of how can we explore space, but the brutally practical question of how can we build a self-sustaining economy in space. The implications of this focused ambition are staggering, and as we begin to piece together the full picture from the research papers and technological demonstrations emerging from this orbiting workshop, it becomes clear that we are not witnessing a simple space race for flags and footprints. We are on the cusp of a new paradigm, a moment when humanity prepares to transition from being visitors in space to becoming permanent residents and builders. The 2 lights in the sky represent 2 paths into that future. One is the path of international science and observation. The other is a path of focused national industrial expansion, and the work being done aboard that second, quieter station may soon redefine our place in the universe entirely. The Heavenly Palace did not rise in a vacuum, either political or historical. Its very existence is a direct answer to a question China was never permitted to ask. May we join you? To grasp the sheer, focused determination behind its construction, we must look back to the dawn of the International Space Station. As the United States and a newly cooperative Russia began piecing together their orbital behemoth in the late 1990s, China was an emerging, yet largely excluded, power in space. The ISS was presented as a global project, but the globe had its limits. Citing concerns over technology transfer and the Chinese program's military roots, Washington kept Beijing at arm's length. The door was never truly open. Then, in 2011, the Wolf Amendment slammed it shut, legally prohibiting NASA from engaging in almost any form of bilateral cooperation with China. The message was unequivocal. China would have to find its own way to the stars. This act of political exclusion became the single most powerful catalyst for the Chinese space program, transforming a national aspiration into an unwavering strategic imperative. Forbidden from participating in the great collaborative effort of the age, China embarked on its own, far quieter, and arguably more methodical path. This was not a reactive scramble for prestige, but the meticulous execution of a plan laid down decades earlier. Known as Project 921, this three-step strategy, conceived in 1992, was China's long march to a permanent human presence in orbit. The first step was to simply prove they could do it, to send a human into space and bring them home safely. This was achieved in 2003, when Yang Liwei orbited the Earth in the Shenzhou 5 capsule, making China only the third nation in history to independently achieve human spaceflight. With the first step secured, the second, more complex phase began, to master the intricate celestial mechanics required to build and operate an orbital outpost. This phase was not about building a palace, it was about learning to lay the foundations. This led to the launch of Tiangong 1 in 2011. The name meant Heavenly Palace, but the reality was far more humble. It was not a sprawling station, but a compact, 8.5-ton cylinder, a Spartan but functional testbed launched in a single piece. Its mission was not grand scientific discovery, but fundamental orbital engineering. It was a school in the sky, designed for one primary purpose: to teach China the delicate art of rendezvous and docking. It was a target vehicle, a lonely beacon waiting for its partners. Over the next 2 years, both uncrewed Shenzhou capsules and, crucially, crewed missions successfully docked with the prototype. It was here that taikonauts practiced the skills that ISS astronauts had been honing for a decade. It was here that Liu Yang became the first Chinese woman in space in 2012. Tiangong 1 was a resounding success in its primary objective, but its end was less graceful. After its mission was complete, ground control lost command, and it made an uncontrolled, fiery re-entry into the atmosphere in 2018, a finale that drew international criticism but provided its own valuable, if harsh, lessons. Learning from both the triumphs and the failures of their first foray, the China National Space Administration launched Tiangong 2 in 2016. This was not a mere repeat of the first. It was a significant upgrade, a true space laboratory. While still a prototype, it was designed to test the next layer of critical technologies. Where Tiangong 1 was about mastering docking, Tiangong 2 was about mastering long-term habitation. It featured more advanced life support systems, paving the way for the regenerative technologies that are now a hallmark of the permanent station. It was on Tiangong 2 that taikonauts conducted the first ever in-orbit refueling tests, a critical capability for maintaining a long-duration outpost. The missions grew longer, with a crew spending 30 days aboard, pushing the boundaries of China's operational experience. They conducted more sophisticated scientific experiments, from quantum communications to plant growth. And when its mission was over in 2019, it performed a perfectly controlled deorbit, burning up over the South Pacific, a quiet demonstration that the lessons of Tiangong 1 had been learned. This deliberate two-step prototype phase stands in stark contrast to the development of the ISS. The International Space Station was built on the fly, a complex multinational construction project where political compromises and budgetary shifts often dictated the engineering timeline. China, unburdened by the need for international consensus, was able to pursue a purely logical, incremental engineering path. Test A, then Test B, then Test C. Each step was a prerequisite for the next. This patient, methodical ascent meant that when the time came to build the final, permanent Tiangong station, it was not an experiment. It was the culmination of a decade of focused practice. They had developed every single component of the required ecosystem in-house. The powerful Long March rockets to lift the modules, the Shenzhou capsules to carry the crew, the Tianzhu cargo ships to act as automated couriers for supplies and fuel, and the expertise to put it all together. This forced self-reliance, born from exclusion, had become their greatest asset. They were beholden to no one, reliant on no foreign supply chains, and masters of their own destiny in orbit. The silent ascent was complete. The stage was set for the real work to begin. With the foundational skills of orbital mechanics and long-term habitation mastered, the true purpose of the Heavenly Palace came into focus. The permanent, multi-module Tiangong, whose construction began in 2021 with the launch of the Tianhe core module, is a testament to this meticulous planning. While the ISS evolved into a laboratory, Tiangong was conceived from the ground up as an integrated research and development platform, a factory for the future. Its scientific agenda is not a disparate collection of curiosities, but a tightly woven 5-point manifesto for humanity's breakout into the solar system. Each of the station's 2 science modules, Wentian and Mengtian, is dedicated to a specific subset of this agenda, and together they form a coherent vision of a self-sustaining off-world economy. The overarching themes can sound deceptively technical: on-orbit assembly, robotics and autonomous systems, new energy and propulsion, regenerative life support, and new spacecraft technologies. But when you unpack what these categories truly mean, you are not looking at a list of experiments. You are looking at the foundational pillars of a spacefaring civilization. The first pillar, on-orbit assembly and construction, is perhaps the most revolutionary. The greatest single constraint on what we can build in space has always been the size of our rocket fairings and the tremendous cost of escaping Earth's gravity well. Every kilogram launched into orbit costs thousands of dollars. China's solution, actively being tested on Tiangong, is simple and profound. Stop launching finished products and start launching raw materials. The station is a testbed for advanced in-space manufacturing techniques, most notably additive manufacturing, or 3D printing. As early as 2018, Chinese scientists pioneered the first successful 3D printing of ceramics in microgravity, a material crucial for heat shields and advanced electronics. Aboard Tiangong, they are refining these processes, experimenting with printing everything from spare parts and tools to structural components. The ultimate goal, laid out in peer-reviewed scientific papers, is to create orbital construction yards that can assemble spacecraft and habitats far larger than anything that could be launched from Earth. Imagine a spacecraft for a Mars mission not being confined to the dimensions of a rocket, but built in orbit, piece by piece, from materials processed in space. This vision extends beyond just assembling prefabricated parts. Tiangong is also a proving ground for deploying large, lightweight structures. Experiments are underway to test inflatable modules, essentially advanced space tents, that can be launched in a compact form and then expanded to create habitats or workshops. These could be deployed as instant infrastructure on the Moon or Mars, far easier to transport than rigid metal modules. Hand in hand with this construction technology is the second pillar, robotics and autonomous systems. Manufacturing, assembly, and maintenance in the harsh vacuum of space are tasks ideally suited for machines. Tiangong is equipped with a sophisticated, 10-meter-long robotic arm that can not only move cargo and assist taikonauts on spacewalks, but also walk around the exterior of the station, moving from anchor point to anchor point. This is the first generation. The experiments being conducted inside the station are developing the second, smaller, more autonomous robots designed for intricate repair work, cargo transfer inside unpressurized modules, and eventually, the automated operation of those orbital factories. The taikonauts are not just crew, they are the trainers and programmers for the robotic workforce that will build the future. The third pillar addresses the fundamental challenge of power and movement across the vast distances of the solar system. Solar panels, the workhorse of the ISS and Tiangong, become increasingly ineffective as you travel away from the sun. By the time you reach Jupiter, sunlight is only 3% as strong as it is in Earth orbit. Anticipating this, China is using Tiangong to research new energy sources, likely including space-based nuclear reactors and more efficient, long-life propulsion systems. But the real game changer is being developed within the station's fourth pillar, environmental control and life support systems, or ECLSS. A truly self-sufficient outpost cannot rely on resupply missions from Earth for water, oxygen, and food. Tiangong's ECLSS is designed from the outset to be regenerative, aiming for a near-perfect closed loop. They are testing advanced systems for recycling urine into potable water and electrolysis units that split water into breathable oxygen and hydrogen. But the most groundbreaking experiment in this domain is one that merges life support with propulsion. At the beginning of 2023, taikonauts aboard Tiangong successfully conducted the first-ever demonstration of artificial photosynthesis in orbit. Using a newly developed semiconductor catalyst, they converted carbon dioxide, the waste product of their own breath, into oxygen and ethylene. Ethylene is a hydrocarbon, a key component in producing rocket fuel. This single experiment represents a paradigm shift. Unlike the energy-intensive oxygen recycling systems on the ISS, this process is more efficient, operates at room temperature, and simultaneously solves two problems. It scrubs CO2 from the air and produces a valuable industrial chemical. Researchers believe the same process can be adapted to create methane, another potent rocket fuel, or even sugars and other organic compounds, effectively mimicking plant life. This is the holy grail of in situ resource utilization, turning the very breath of the crew into the fuel that can take them to their next destination. Add to this the ongoing experiments with growing rice and other vegetables in space, and the picture of a self-sufficient deep space habitat becomes startlingly clear. Finally, the fifth pillar, testing new generic spacecraft technology, ties it all together. Every new pump, valve, sensor, and computer system is put through its paces in the unforgiving microgravity and radiation environment of low Earth orbit. Fluid dynamics, in particular, behave in profoundly non-intuitive ways without gravity, and Tiangong is a dedicated laboratory for understanding and engineering systems that can reliably manage liquids, from coolants to propellants, in this alien environment. When you assemble these 5 pillars, the ambition is no longer subtle. Orbital 3D printing, autonomous construction robots, advanced power and propulsion, the ability to turn waste air into rocket fuel, and a vast catalog of space-hardened components. This is not a plan for a flag-planting mission to the moon. It is the detailed, systematic development of the technological infrastructure required to build and sustain a permanent, industrial human presence throughout the solar system, capable of mining asteroids, building its own ships, and living off the land, wherever that land may be. While the Heavenly Palace was born from a doctrine of focused self-reliance, its international counterpart rose from the ashes of a global rivalry. The International Space Station is not merely a laboratory, it is a political and engineering miracle, a monument to an unprecedented and perhaps unrepeatable era of global cooperation. Its genesis lies in the collapse of the very conflict that first propelled humanity into space. In the 1980s, the Cold War raged on, and the two superpowers envisioned their own separate empires in the sky. The United States was designing Space Station Freedom, a grand American outpost. The Soviet Union was planning Mir 2, a successor to its already operational Mir station. Both were nationalistic projects, symbols of technological supremacy. But then, the Berlin Wall fell, and the Soviet Union dissolved. Suddenly, the geopolitical landscape and the budgets that came with it were radically transformed. The justification for colossal, single-nation space projects evaporated. In the ensuing geopolitical realignment, a brilliant and audacious idea took shape. The bitter space race could be transformed into a collaborative peace dividend. Bringing the nascent Russian Federation into a joint space station project was a masterstroke of statecraft. It provided a common, high-minded goal that could bind former adversaries. More pragmatically, it kept thousands of highly skilled Russian rocket scientists and engineers gainfully employed on a peaceful project, preventing a potential brain drain to rogue states seeking their expertise. The ISS, therefore, was conceived as much as a tool of foreign policy as it was a platform for science. It was a handshake in orbit, a conscious decision to build something together that was too expensive and too complex for any one nation to build alone. This spirit of cooperation expanded, eventually encompassing 15 nations, including the European Space Agency, Japan, and Canada, each contributing their unique technological prowess. The sheer scale of the undertaking was, and remains, breathtaking. Spanning an area the size of an American football field and weighing over 450 tons, the ISS is the single most expensive object ever built, with a price tag north of $150 billion. It was an impossibility to launch such a behemoth in one go. The station had to be a modular puzzle, assembled piece by piece, 400 kilometers above the Earth, while traveling at 28,000 kilometers per hour. Components built in factories in Alabama, Moscow, Turin, and Tokyo, often using different measurement systems and engineering philosophies, had to mate with micron-perfect precision in the unforgiving vacuum of space. The logistical ballet involved dozens of launches on 3 different types of vehicles: America's powerful space shuttles and Russia's reliable Soyuz and Proton rockets. In a testament to the engineers involved, every single launch carrying a primary component of the station was successful. The construction began in earnest in November 1998, when a Russian Proton rocket carried the first module, Zarya, into orbit. Zarya, meaning dawn, was the station's initial powerhouse, providing propulsion, guidance, and power from its modest solar arrays. It was a lonely outpost for just 2 weeks. Then, in December, the Space Shuttle Endeavour roared into orbit carrying the American-built Unity node. This was the moment of truth. Using the shuttle's robotic canadarm, astronauts gingerly plucked the 12-ton Unity module from the cargo bay, positioned it, and then meticulously maneuvered the entire shuttle to guide Unity's docking port onto Zarya's. The successful connection of these 2 modules, one Russian and one American, was the symbolic and literal foundation of the entire station. But it was still just an unlit, unlivable shell. That changed in July 2000 with the arrival of the Russian Zvezda service module. Zvezda, or Star, was the station's heart and brain. It contained the first crew quarters, the primary life support systems, and the main command and control functions. With Zvezda securely docked, the ISS was finally ready for its inhabitants. On November 2, 2000, a Soyuz capsule carrying Russian cosmonauts Yuri Gitsenko and Sergei Krikalev, alongside American astronaut Bill Shepard, docked with the fledgling station. As the hatch swung open and they floated aboard, they became Expedition 1, the first of an unbroken chain of human crews. From that day forward, the International Space Station has never been empty. Humanity had secured its permanent foothold in the cosmos. Over the next decade, the station grew with astonishing speed. The central backbone, the integrated truss structure, was painstakingly assembled, providing the mounting points for the station's most vital systems. 4 massive pairs of solar arrays were unfurled, their double-sided panels capturing both direct sunlight and light reflected from the Earth, generating enough electricity to power dozens of homes. A new, more advanced robotic arm, Canadarm2, was installed. Unlike its shuttle-based predecessor, this arm could walk end over end across the station's exterior, becoming the primary workhorse for all future construction and maintenance. Laboratory modules from the United States, Destiny, Europe, Columbus, and Japan, Kibo, were added, transforming the outpost into a world-class research facility. The ISS was no longer just a symbol of cooperation. It was a bustling, sprawling city in the sky, a testament to the logistical miracles that can be achieved when nations choose to build bridges instead of walls. The construction of the International Space Station was a triumph of macro-engineering, a story told in rocket launches and robotic arms. But the true ongoing drama of the ISS unfolds on a far more intimate scale. It is a biological war waged within the bodies of every astronaut who calls the station home. Life in orbit is a relentless, moment-to-moment battle against the fundamental laws of physics and biology. The human body is a masterpiece of evolution, exquisitely tuned over millions of years to the constant crushing embrace of Earth's gravity. When that force is stripped away, the body doesn't simply relax, it begins to dismantle itself with ruthless efficiency. The primary adversary in this war is microgravity. It is not the absence of gravity, but a state of perpetual free fall, a constant falling around the curve of the Earth. To the body's internal systems, this is a signal that the rules have changed, and the carefully calibrated machine of human physiology starts to execute a series of adaptations that are perfectly logical for space, but catastrophic for a return to Earth. The most immediate and dramatic assault is on the musculoskeletal system. On Earth, every step, every movement, every simple act of standing upright sends signals through our bones and muscles, telling them they are needed. This mechanical loading is the trigger for bone regeneration and muscle maintenance. In the weightless environment of the ISS, that signal goes silent. The body, following a brutal use it or lose it logic, begins to deconstruct the now superfluous structures. The bones undergo a rapid form of osteoporosis. Specialized cells that break down old bone tissue continue their work, but the cells responsible for building new bone become dormant. Astronauts can lose between 1 and 2% of their bone mass per month in critical weight-bearing areas like the pelvis and the lower spine. To put that in perspective, an elderly person with severe osteoporosis on Earth might lose that much in an entire year. Without countermeasures, a 6-month mission could inflict a decade's worth of aging on an astronaut's skeleton. Simultaneously, the muscles begin to waste away. The large, powerful anti-gravity muscles of the legs and back, which work constantly on Earth just to keep us standing, are suddenly unemployed. They atrophy with shocking speed. The heart, a muscle itself, also adapts. On Earth, it must work tirelessly to pump blood uphill to the brain against the pull of gravity. In space, that resistance vanishes. The heart doesn't have to work as hard, and so, like any underused muscle, it shrinks and weakens, becoming slightly more spherical in shape. To combat this systematic decay, life on the ISS revolves around a mandatory, punishing exercise regime. For up to 2 hours every single day, astronauts must subject their bodies to artificial stress. They run on a treadmill, strapped down by a harness of elastic bungees to simulate body weight. They use the Advanced Resistive Exercise Device, or ARED, a complex machine that uses vacuum cylinders to create resistance, allowing them to perform squats, deadlifts, and bench presses in an environment where a 200-kilogram weight would have no mass. This is not fitness, it is medicine. It is a daily, exhausting prescription to trick their bodies into not consuming themselves. The war is also fought in the circulatory and nervous systems. On Earth, gravity pulls bodily fluids down into our legs. In space, this fluid shifts upwards, pooling in the torso and head. This is why astronauts in their first days in orbit often have puffy, swollen faces and congested sinuses, a condition they call fat face, accompanied by spindly chicken legs. The body, sensing this fluid overload in the upper torso, misinterprets it as having too much blood and triggers a response to excrete excess water and salt. Within days, an astronaut's total blood volume can drop by as much as 20%. This fluid shift is also responsible for one of the most insidious and poorly understood threats to long-duration spaceflight: spaceflight-associated neuroocular syndrome, or SANS. The increased fluid pressure in the skull can physically reshape the back of the eyeball, flatten the optic nerve, and cause vision problems. Some astronauts have returned to Earth with permanent changes to their eyesight, a chilling reminder that we are still discovering the myriad ways the void can harm us. Even the brain is thrown into a state of profound confusion. The vestibular system in the inner ear, our biological gyroscope that gives us our sense of up and down, becomes utterly useless in freefall. It sends a stream of nonsensical data to the brain, which violently conflicts with what the eyes are seeing. The result for about half of all astronauts is space adaptation syndrome, a debilitating form of motion sickness that can last for several days, turning their initial experience of weightlessness into a miserable ordeal of nausea and disorientation. Every aspect of daily life, from the mundane to the critical, is complicated by this hostile environment. You can't simply drink a cup of coffee. You must sip it from a sealed pouch to prevent droplets from floating away and short-circuiting a million-dollar piece of equipment. Sleeping requires strapping oneself into a vertical sleeping bag tethered to a wall to avoid drifting into a control panel. The human body is the most fragile and complex experiment aboard the station, and every astronaut is a data point, their own physiology the subject of constant monitoring and study. They are not just living in space, they are actively fighting it every minute of every day just to remain whole. The International Space Station, for all its engineering grandeur, is ultimately defined by the science it makes possible. It is a laboratory unlike any on Earth, precisely because it has removed the single most dominant variable in any terrestrial experiment: gravity. This is not merely about making things float. It is about peeling back a fundamental force of nature to observe the universe in its raw, unfiltered state. In the constant freefall of orbit phenomena that are fleeting, subtle, or completely masked by gravity's relentless pull, on Earth suddenly takes center stage. The ISS becomes a unique window into the hidden mechanics of reality, revealing secrets in everything from a simple candle flame to the very fabric of space-time and the nature of the cosmos's missing matter. The most profound discoveries often begin with the most mundane observations, and in microgravity, even the familiar becomes alien and deeply instructive. Consider fire. On Earth, we have an innate, primal understanding of a flame. It is a flickering, teardrop-shaped spear of light that always reaches upward. This shape is not an intrinsic property of combustion. It is a direct consequence of gravity. The flame heats the air around it, making it less dense. Buoyancy, a product of gravity, forces this hot air to rise, drawing in cooler, oxygen-rich air from below. This constant convective flow is what gives a flame its shape and its vigor. Aboard the ISS, this entire process vanishes. When an astronaut ignites a droplet of fuel, the resulting flame is not a teardrop, but a dim, shimmering sphere. Without gravity, there is no up. The hot gases do not rise, and there is no convective current to feed the fire. Instead, oxygen must slowly and inefficiently diffuse towards the flame from all directions. The result is a cooler, slower, and often nearly invisible burn. This isn't just a curious parlor trick, it is vital research. Understanding this fundamental behavior of combustion is critical for spacecraft fire safety and for designing more efficient and cleaner combustion engines back on Earth. The same principles that reshape fire also warp the behavior of fluids. Attempting something as simple as boiling water in space becomes a complex physics experiment. On Earth, convection carries the small bubbles of steam from a heated element up through the water, allowing for efficient heat transfer. In space, without convection, those small bubbles coalesce around the heating element, forming a single, large, insulating bubble of vapor. This vapor layer prevents the surrounding water from reaching the heat source, effectively stopping the boiling process. This presents a massive engineering hurdle for future long-duration missions, which will rely on fluid-based systems for cooling, life support, and propulsion. Propellers moving through liquids also behave differently, creating cavitation, the formation and violent collapse of vacuum bubbles, in ways that are difficult to model on Earth. Research into this phenomenon aboard the ISS, designed to make spacecraft pumps more durable, led to one of the most astonishing intellectual leaps in modern astrophysics. Scientists realized that the physics governing the collapse of these tiny, gravitationally unhindered bubbles provided a startlingly accurate model for a previously unexplained type of supernova, where the core of a dying star sloshes around before imploding. A microscopic event inside a box on the ISS helped illuminate one of the most cataclysmic explosions in the universe. From the familiar made strange, the ISS also pushes into realms of physics that are entirely alien to our everyday experience. It is home to the Cold Atom Lab, a facility that can achieve temperatures just a whisper above absolute zero, 1,000,000,000 times colder than deep space. In this extreme cold, atoms slow to a crawl and begin to lose their individual identities, overlapping until they behave as a single quantum entity, a fifth state of matter known as a Bose-Einstein condensate, BEC. On Earth, gravity tears these fragile quantum clouds apart in milliseconds. Aboard the ISS, they can float and persist for many seconds, allowing for sustained and detailed study. The crew has even managed to create hollow, bubble-like BECs, macroscopic objects that obey the bizarre rules of quantum mechanics. This research is not purely academic. It is the foundation for a future generation of ultra-precise technologies, including atomic clocks and sensors capable of detecting minute shifts in gravity. The long-term goal is to build atom interferometers in space, devices that could detect gravitational waves in a frequency range that ground-based observatories like LIGO cannot, potentially revealing the mergers of different kinds of black holes and probing the intersection of quantum mechanics and gravity itself. At the other end of the spectrum, while the Cold Atom Lab explores the universe at its coldest, another external experiment, the Alpha Magnetic Spectrometer, AMS, studies its most energetic particles. Bolted to the station's main truss, the AMS is essentially a giant particle detector in space. It sifts through the constant rain of high-energy cosmic rays that bombard the Earth, particles accelerated to near light speed by distant supernovae and other violent cosmic events. Its primary mission is one of the most profound in all of science: the hunt for dark matter. We know from the rotation of galaxies that the visible universe of stars and gas makes up only a fraction of the total mass. The rest is an invisible, unknown substance. The AMS is searching for the annihilation signature of a leading dark matter candidate particle. If these particles exist, they should occasionally collide and destroy each other, producing a telltale excess of other particles, like positrons and antiprotons, at specific energies. For over a decade, the AMS has been meticulously counting billions of cosmic ray events, searching for that faint signal that would finally unveil the nature of the universe's missing 85%. From the quiet flicker of a spherical flame to the violent echo of a dying star, from the coldest atoms imaginable to the most energetic particles in the cosmos, the ISS provides the one laboratory where gravity's grip is loosened, allowing the deeper secrets of the universe to float to the surface. For all the research that pushes our understanding outward into the cosmos, perhaps the most profound and enduring legacy of the International Space Station will come from its steady, introspective gaze back upon our own world. From its vantage point 400 kilometers high, the ISS is humanity's greatest watchtower, a sentinel offering a perspective that is both deeply philosophical and critically scientific. This dual vision begins in the cupola, the station's 7-windowed bay that looks down upon the Earth. It is here that astronauts experience the overview effect, a cognitive shift reported by space travelers since the Apollo era. Through these windows, the Earth is not a map of competing nations with bold, colored borders. It is a single, seamless entity, a living, breathing organism of swirling white clouds, deep blue oceans, and patchwork continents. It is a shared home, shockingly fragile, its vibrant life protected only by a gossamer-thin, electric blue line of atmosphere. This visceral experience of seeing our world without its artificial divisions is in itself a powerful return on the investment in the station. It is a constant reminder of our shared destiny. But this philosophical perch is also a world-class scientific platform. The ISS is not just a window. It is a powerful, multispectral lens for diagnosing the health of our planet. Its unique orbit, inclined at 51.6 degrees, means it passes over more than 90% of the Earth's populated areas, tracing a different path with each 90-minute lap. This provides a dynamic, ever-changing view that complements the fixed pole-to-pole orbits of most dedicated Earth observation satellites. The station's instruments are not just passively observing, they are conducting a planetary-scale physical. The Japanese experiment module, Kibo, for example, features an external terrace exposed to the vacuum of space. This facility is home to an array of Earth-facing sensors, including a powerful hyperspectral imager. A standard camera sees the world in 3 colors: red, green, and blue. A hyperspectral camera sees it in hundreds of narrow, contiguous bands of the electromagnetic spectrum. This allows scientists to move beyond simply taking a picture and instead perform detailed chemical analysis from orbit. They can identify the unique spectral fingerprint of different minerals, assess the health of crops by detecting subtle changes in chlorophyll, track the spread of pollutants in coastal waters, and map the biodiversity of a rainforest with astonishing precision. This diagnostic power is a recurring theme. Mounted on the station's exterior is an instrument called EcoStress, which stands for Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station. Its mission is to measure the temperature of plants. This might sound simple, but it is a revolutionary tool for managing Earth's most precious resource, water. Just as humans sweat to cool down plants, release water through tiny pores in their leaves in a process called transpiration. When a plant is stressed by heat or lack of water, these pores close up and the plant's temperature rises. EcoStress can detect these minute temperature changes with incredible accuracy, effectively taking the temperature of Earth's vegetation field by field. This data provides an early warning system for farmers, helping them to irrigate more efficiently, and for scientists tracking the impact of droughts on forests and natural ecosystems. It is a global thermometer for the biosphere, helping us understand which parts of our world are beginning to run a fever. The station also serves as a crucial tool in the global effort to understand climate change. The Orbiting Carbon Observatory 3, also known as OCO-3 instrument, mounted on Kibo's terrace, is mapping the concentration of carbon dioxide in the atmosphere with unprecedented detail. By tracking the sources of CO2, like cities and industrial areas, and the sinks that absorb it, like forests and oceans, on a daily basis, it helps to build a far more detailed picture of the global carbon cycle. This is not just about confirming that climate change is happening, it is about providing the high-resolution data needed to create more accurate climate models and to verify the effectiveness of efforts to reduce emissions. When a hurricane forms over the Atlantic, a wildfire rages in California, or a volcano erupts in Indonesia, the ISS often becomes a first responder. Astronauts with their own eyes and high-powered cameras can provide unique, real-time imagery to disaster relief agencies on the ground. The station's unpredictable orbital path means it can capture views of a developing crisis from different angles and at different times of day than a standard satellite, providing crucial context for emergency planners. And in this era of advanced automation, the human element remains irreplaceable. The Crew Earth Observations program has been running since the first space station missions. It leverages the single most powerful pattern recognition computer we know of, the human brain. An astronaut can look out the window and spot a fleeting transient event, a phytoplankton bloom, a developing dust storm, the sun glint off a remote body of water, that an automated sensor might be programmed to ignore. With a handheld digital camera and a telephoto lens, they can capture images with a resolution and contextual awareness that are often superior to satellite data for specific scientific targets. This synergy between human intuition and robotic precision makes the station an unparalleled observatory. From its orbital perch, the ISS helps us to not only soar from the Earth, but to better understand and care for the ground upon which we walk. It is our watchful eye, reminding us that for all our ambitions to reach for the stars, our most important mission will always be the stewardship of the fragile blue marble below. In the silent orbital theater above our heads, the two great stations perform their nightly traverse, but they are dancing to profoundly different rhythms. They represent more than just competing national programs or different engineering philosophies. They are the physical embodiment of a fundamental divergence in humanity's approach to the cosmos, a schism in the strategy for our species' next great leap. The International Space Station, for all its complexity, represents a mission of introspection and observation. It is a laboratory that primarily looks inward at the fragile human body, inward at the fundamental laws of physics, and inward, with a watchful and loving eye, back upon the Earth. Tiangong, the heavenly palace, is its conceptual opposite. It is an outpost of extroversion and preparation. Its gaze is fixed firmly outward and forward, not asking what we can learn about the universe as it is, but asking how we can fundamentally alter our relationship with it, transforming ourselves from visitors into builders. One is a cosmic university. The other is a frontier workshop. The ISS is the ultimate destination for the science of self-discovery. The decades of research into the devastating effects of microgravity on bone density, muscle mass, and cardiovascular health are a profound study of our own biological limitations. It is an inward journey into the very code of our terrestrial evolution, cataloging every way in which our bodies rebel against the void. Its purpose is to understand the price of admission to space, to map the boundaries of our endurance so that we might survive longer voyages. Similarly, its most advanced physics experiments are acts of deep contemplation. The alpha magnetic spectrometer sifts the cosmic rays for clues to dark matter, looking inward at the universe's fundamental composition. The Cold Atom Lab slows matter to a quantum standstill, probing the very nature of reality at its most granular level. These are experiments that seek to understand, not to build. They are the work of a species holding a mirror up to the cosmos to better see itself. And nowhere is this introspection more evident than in its constant surveillance of our home world. The station's greatest service is arguably as a planetary diagnostics tool, its sensors and cameras charting the health of our oceans, forests, and atmosphere. The ISS is the culmination of the first age of space exploration, a magnificent platform for learning to live in our orbital backyard and for appreciating the home we left behind. Tiangong operates under a starkly different mandate. If the ISS is a university, Tiangong is a polytechnic institute for celestial engineering. Its experiments are not designed to map our biological limits, but to create the technologies that will make those limits irrelevant. While ISS astronauts meticulously study bone loss, taikonauts are perfecting the regenerative life support systems that will create fully independent biospheres, closing the loop on water, air, and waste. They are not just surviving, they are practicing self-sufficiency. This is the difference between writing a dissertation on the challenges of frontier life and actually forging the axe, designing the plow, and building the grain silo. The research aboard Tiangong is a direct, pragmatic assault on the tyranny of the rocket equation and the logistical nightmare of deep space travel. The groundbreaking experiment in artificial photosynthesis, turning exhaled carbon dioxide into oxygen and rocket fuel precursors, is a prime example. This is not science for the sake of understanding a chemical process. It is the development of a core technology for in situ resource utilization. It is a dress rehearsal for living off the land on Mars or the Moon, turning a liability, waste CO2, into a critical asset. The entire research agenda of the Heavenly Palace is a checklist for cosmic industrialization. The development of orbital 3D printing is not about making a few spare parts. It is about proving the viability of in-space manufacturing, the first step toward building massive structures and spacecraft in orbit, free from the constraints of being launched from Earth. The testing of autonomous robotics is not about convenience. It is about creating the tireless, radiation-hardened workforce that will assemble those structures and mine the resources to feed them. Every major experiment aboard Tiangong can be understood as a foundational patent application for the technologies of a spacefaring economy. It is a station that is less concerned with the why of the universe than the how of conquering it. It looks outward, not with the contemplative gaze of an astronomer, but with the keen eye of a prospector, an engineer, and a pioneer. It is the vanguard of the second age of space exploration, an age not of visitation, but of settlement and expansion. This divergence is the great untold story of our current moment in space. We have one station dedicated to understanding our limitations and appreciating our home, a monument to a global scientific commons. We have another dedicated to systematically breaking free of those limitations and building new homes, a testament to focused national ambition. One is the final, glorious chapter of humanity learning to survive in space. The other is the first declarative chapter of humanity learning to thrive there. Both are essential. We must understand the price of the journey, and we must build the tools to pay it. But as these two silent lights continue their nightly passage, they trace two very different paths across the sky. And they are leading humanity toward two very different and potentially spectacular futures. As the International Space Station approaches its planned retirement in the early 2030s, the era of grand multinational collaboration in low Earth orbit is drawing to a close. Its fiery, controlled descent into the Pacific Ocean will mark the end of an epoch. But the spirit of cooperation that it fostered, the very model of an international partnership in the cosmos, is not dying. It is evolving and moving outward. The next great collaborative frontier is already under construction, not in the familiar skies above our heads, but in the silent, empty vastness of cislunar space. It is called the Lunar Gateway, and it represents both the spiritual successor to the ISS and a radical redefinition of what a space station is for. Where the ISS was a destination, a city in the sky, Gateway will be a transfer station, a remote mountain outpost, a harbor on the shores of the deep cosmic ocean. The Gateway is a cornerstone of NASA's Artemis program, the ambitious plan to return humans to the moon, this time to stay. But it is not a purely American endeavor. Like the ISS, it is a joint effort with the European Space Agency, the Japanese Aerospace Exploration Agency, and the Canadian Space Agency CSA as primary partners. Each agency is contributing critical components, leveraging the decades of experience gained from building and operating the ISS. ESA is providing the primary habitat module, IHAB, and a communications and refueling module, ESPRIT. JAXA is contributing advanced life support systems and cargo transport capabilities. And Canada, once again, is providing the station's robotic heart with Canadarm3, a next-generation autonomous robotic system that will be indispensable for maintenance and operations at a station that, for most of its life, will be completely uncrewed. This last point marks the most fundamental difference between Gateway and the ISS. The ISS was designed for permanent human habitation. Gateway is designed for Spartan functionality and robotic autonomy. It will be much smaller than the ISS, a minimalist outpost comprising initially just a power and propulsion element and a small habitat. Its purpose is not to be a home, but a staging post. It will serve as a command center for lunar surface missions, a docking port for Orion crew capsules arriving from Earth, a transfer point for astronauts moving to lunar landers, and a science laboratory for studying the deep space environment outside the protective bubble of Earth's magnetosphere. This is a crucial distinction. The ISS orbits within the Van Allen belts, which shield it from the worst of solar and cosmic radiation. Gateway will have no such protection. It will be a proving ground for the technologies and radiation shielding necessary to keep astronauts safe on long-duration missions to Mars and beyond. Its orbit is also a work of celestial genius, a far cry from the simple circular path of the ISS. Gateway will be placed in a near-rectilinear halo orbit, NRHO, a highly elliptical, 7-day loop around the Moon. At its closest point, it will skim just 3,000 kilometers above the lunar North Pole. At its furthest, it will swing out 70,000 kilometers beyond the lunar South Pole. This unique trajectory offers several key advantages. It is gravitationally stable, requiring minimal fuel for station keeping. It provides constant line-of-sight communication with Earth. and crucially, it offers unprecedented access to the entire lunar surface, particularly the shadowy, ice-rich craters of the Moon's south pole, the primary target for Artemis surface missions. The station will act as a relay, a communications hub connecting the lunar south pole, which is often hidden from Earth's view, with mission control in Houston. The construction of Gateway will mirror the modular approach of the ISS, but on an accelerated and more technologically advanced timeline. The components will be launched not on dozens of separate flights, but primarily by heavy-lift commercial rockets like SpaceX's Falcon Heavy and NASA's own Space Launch System, SLS. The first two elements, the Power and Propulsion Element, PPE, and the Habitation and Logistics Outpost, HALO, will be launched together, docking autonomously in deep space to form the station's initial core. Unlike the ISS, which relied on the Space Shuttle's robotic arm for its initial assembly, Gateway will essentially build itself, with its first modules designed to find each other and connect without human intervention. This reliance on advanced automation and robotics is the key to its existence. With crews only visiting for short durations, perhaps once a year, Gateway must be able to maintain and even repair itself for long periods. A critical test of the systems that will be needed for future, even more remote outposts around Mars. The Gateway, therefore, represents the lessons of the ISS distilled and projected into a new, more challenging arena. It takes the model of international cooperation and applies it to a mission of exploration rather than just occupation. It leverages the modular construction techniques but replaces the need for constant human oversight with sophisticated robotics and AI. It is a leaner, tougher, and more strategically focused platform. While the ISS taught us how to live together in our planetary backyard, Gateway is designed to be the base camp from which we will learn to explore the vast wilderness beyond. It is the next logical step in the collaborative human journey into space, a testament to the idea that while one nation might reach for the moon, it takes a global village to build a permanent road there. While the international consortium led by NASA charts its deliberate, collaborative course back to the moon with the Gateway, China is pursuing its own parallel path to the cosmos, and its roadmap has two equally ambitious primary destinations. The West's Artemis program is a sequential journey. Master the moon first, then use those lessons to reach for Mars. China's strategy is more of a concurrent assault on two fronts. They see the moon not merely as a goal in itself, but as an indispensable industrial proving ground. While their work in low Earth orbit is already a direct and sophisticated dress rehearsal for the Red Planet, every screw turned, every system tested, and every experiment conducted aboard the Tiangong space station is a calculated step towards a future where the red flag flies not just over a lunar outpost, but over a permanent human settlement on Mars. The Heavenly Palace is not an Earth-orbiting laboratory. It is Mars Mission Control, a high-fidelity simulator for the longest and most dangerous voyage humanity has ever contemplated. China's lunar ambitions are embodied in the planned International Lunar Research Station, ILRS, a project it is spearheading with Russia and other partners. While it echoes the collaborative spirit of the ISS, its purpose is far more aligned with Tiangong's industrial ethos. The ILRS is envisioned as a permanent, robotic, and eventually human-tended base at the lunar South Pole. Its mission is not simply to collect rocks and plant flags, but to begin the process of living off the land. This is where the technologies being honed on Tiangong will face their first true off-world test. The 3D printers will be tasked with turning lunar regolith, the moon's dusty soil, into bricks, landing pads, and radiation shields. The autonomous robots will be deployed to prospect for and mine the water ice trapped in the permanently shadowed craters. And the life support systems will be challenged to operate in a true deep space radiation environment, recycling resources far from the safety of Earth's magnetosphere. The ILRS is the practical exam for the theoretical knowledge being gathered on Tiangong. But even as they plan this lunar industrial park, The taikonauts in orbit are already living on Martian time. The greatest single challenge of a human mission to Mars is not getting there, but surviving the journey and having the ability to come back. A round trip could take up to 3 years. A logistical umbilical cord to Earth is simply not feasible. The mission must be almost entirely self-sufficient, and Tiangong is where that self-sufficiency is being born. Consider the absolute necessity of a closed-loop life support system. The ISS's system is a marvel, but it is not perfect. It still requires regular resupply of water and other consumables. For a 3-year Mars mission, almost perfect is a fatal flaw. The advanced regenerative ECLSS being tested on Tiangong, with its goal of near total water and oxygen recovery, is not an incremental improvement. It is the mandatory enabling technology for interplanetary travel. Then there is the tyranny of propellant. Getting a crew to Mars is hard. Launching enough fuel with them to get them home again is almost impossible with current technology. This is where the seemingly niche experiment in artificial photosynthesis becomes the key that unlocks the entire mission architecture. The Martian atmosphere is over 95% carbon dioxide. It is a thin, unbreathable poison to humans, but to the catalytic process tested on Tiangong, it is a vast, waiting resource. A future Mars mission based on this technology would land an automated system first. This system would breathe in the Martian CO2, and, using power from solar arrays or a small nuclear reactor, convert it into oxygen for the crew to breathe, and methane, a potent rocket fuel, for the ascent vehicle. The crew would arrive to find their ride home already waiting in the tank, manufactured from the Martian air itself. The experiment on Tiangong that turned a taikonaut's breath into ethylene was not a curiosity. It was the first successful demonstration of the core chemical reaction that makes a return trip from Mars viable. Every other pillar of Tiangong's research aligns with this singular focus. The in-space manufacturing techniques are for printing critical replacement parts millions of kilometers from Earth, where the nearest hardware store is a year-long journey away. The autonomous robots are the advanced scouts and construction workers that will prepare a habitat before the fragile humans ever arrive. The research into new, high-efficiency propulsion is a direct response to the need to shorten the transit time, reducing the crew's exposure to the deadly G-force of galactic cosmic rays. The entire Tiangong project can be viewed as a systematic campaign to de-risk a Mars mission. While the West debates budgets and builds international consensus, China is quietly, methodically, and relentlessly solving the engineering problems. The taikonauts are not just orbital researchers, they are the first Martians in training, mastering the systems, enduring the isolation, and proving the technologies that will carry humanity to its next planetary foothold. The Red Dragon's ambitions are not confined to the silvery light of the moon. They are cast in the unmistakable, ruddy glow of Mars. We are standing at a biological and technological threshold unparalleled in the history of life on Earth. For 4 billion years, life has been a purely planetary phenomenon, bound by the gravity and atmosphere of its terrestrial cradle. But now, for the first time, a single species has developed the capacity to consciously sever that umbilical cord. The silent, ceaseless work being conducted in the orbiting laboratories above is not merely the next chapter in the story of exploration. It is the preface to a new genesis, the moment our species prepares to leave the nest, not for a brief flight, but for good. The great divergence between the ISS and Tiangong is not a sign of a fractured future, but of a maturing one. It is the natural division of labor required for any great migration. One group meticulously studies the map and the terrain, while the other forges the tools and packs the wagons. The International Space Station has been our map maker. For 2 decades, it has been the school where we learned the harsh lessons of the void. It taught us, in excruciating detail, about our own physical fragility. It was the biological crucible that revealed the enemy was not just the vacuum and the radiation, but the subtle, relentless rebellion of our own bodies against an environment for which they were never designed. It was the observatory that gave us the clearest perspective on the preciousness and vulnerability of the home we were preparing to leave behind. The ISS answered the essential preliminary questions. What are the dangers? What are our limits? What is at stake? It provided the foundational knowledge, the textbook of survival, written in the language of bone densitometry and fluid shifts, of astrophysics and climate science. It was the contemplative, cautious, and necessary first step. Tiangong is the second step, the practical application of that hard-won knowledge. It is the workshop where the tools for the Great Migration are being engineered and perfected. It represents the pivot from understanding the problem to building the solution. The taikonauts are not just cataloging the challenges of self-sufficiency, they are demonstrating its reality. The artificial photosynthesis that turns waste air into fuel. The regenerative life support systems striving for a perfect closed loop. The 3D printers that promise to turn asteroid dust into spacecraft hulls. The autonomous robots that will be the tireless builders on alien worlds. These are not theoretical experiments. They are the component parts of the engine of expansion. They are the practical answers to the questions the ISS posed. How do we overcome our biological limits? We build self-sustaining biospheres. How do we conquer the vast distances? We learn to live off the land and make our own fuel. How do we build the infrastructure of a new civilization? We create a workforce of machines that can operate where humans cannot. Tiangong is the manifestation of a species that has finished its studies and has now rolled up its sleeves to begin the work. This is the great work of our time. The combined efforts in orbit, both collaborative and independent, are forging the key technologies that will transform humanity into a multiplanetary species. The moon is the immediate goal, but it is not the ultimate prize. It is the final proving ground, the shakedown cruise for the ships and systems that will carry us further. The lunar bases envisioned by both the Artemis Accords and the ILRS are the shipyards where we will learn to build and provision the vessels for the truly great voyages. They are the low-gravity construction platforms where we will assemble the first true interplanetary craft, far too large and complex to ever be launched from the deep gravity well of Earth. The water ice at the lunar poles will not just be for drinking, it will be cracked into hydrogen and oxygen, the rocket fuel for the Martian fleet. We are witnessing the birth of a new human diaspora. For thousands of years, our ancestors spread across continents, driven by climate, curiosity, and competition. Now, we are preparing to spread across worlds, driven by the same ancient urges, but armed with technologies that were science fiction only a generation ago. This is more than a hedge against terrestrial catastrophe. It is the fulfillment of an evolutionary imperative, the scattering of the seeds of consciousness to ensure their survival on a cosmic scale. The two lights in the sky are no longer just symbols of national pride or scientific curiosity. They are the silent forges of our future, the twin engines of a species preparing for its own self-directed genesis. They are the proof that we are no longer just looking at the stars. We are packing for the journey. The next time you stand under a clear night sky and see a steady, silent star glide across the firmament, know that you are not just watching a satellite. Those 2 points of light, the aging Grand Cathedral of the ISS and the focused humming forge of Tiangong, are the active construction sites of tomorrow. They are the places where humanity is quietly, methodically, and relentlessly solving the final problems that stand between us and a future amongst the planets. The work being done up there, in the silence and the freefall, transcends politics and headlines. It is the slow, deliberate untethering of life from its home world. What began as a rivalry of empires and evolved into a monument of cooperation has now entered a new phase, a determined, practical preparation for exodus. We are living in the brief, pivotal moment between a purely terrestrial past and an interplanetary future. The lights in our sky are no longer just symbols of how far we have come. They are the beacons guiding us to where we are going, engaged in the quiet, steady work of becoming infinite.